Hello, everyone, and welcome to Physics 212, Lab 5. In this lab, we're going to be measuring the acceleration due to gravity. So we're going to be measuring g. And actually, we're going to do that in CGS units. So hopefully, we will get values close to the accepted value, which is 980 centimeters per second squared. Now, how are we going to measure g? We're going to do this two different ways. One way is using a ball drop apparatus. And the second way is using a simple pendulum, right? So those wooden pendulums, or you could even use a simulation like the PHET simulation of a pendulum. That would also work. So first of all, make sure you watch my short little video where I show you how I actually collected the data using the equipment, using the ball drop apparatus equipment. Right? Otherwise, it won't make as much sense until you actually see that video and see the equipment itself. So the idea is pretty simple here. We have this setup, and again, you'll see this when you watch the video of the equipment itself. We have this ball dropper. I tried to diagram it here. And then a first photogate, which we're going to call photogate A, is placed at 15 centimeters below the ball dropper. Okay, so that stays there. And then below that is going to be photogate B, the second photogate, and its position is going to vary. Okay, so this delta x12, this is going to be the distance from that first photogate A to the second photogate B. And we're going to vary it. We're going to have it at 10 centimeters below the photogate A, then it'll be 20 centimeters below, then 30, 40, 50, right? So there's basically 5 conditions. That distance is going to vary. Now, given the information from the photogate timers, we can calculate the velocity of the ball as it passes through photogate A, that's called VA here. And we can also calculate the velocity of the ball just at the instant as it passes through photogate B, which we're calling VB. Now, we know also the time it takes to go from that first photogate A, to the second photogate B. And we're calling that delta T12. Think of 12 as meaning from the first position to the second position. We could have also said AB, okay? So it's the time that it takes to go from the first to the second photogate. So if we know the velocity at photogate A, we know the velocity at photogate B, and we know the time it takes to go from photogate A to photogate B, that's enough information to calculate the acceleration, right? So here's sort of the main idea. Remember, the average acceleration in general is defined to be the change in velocity. So it's the final velocity minus the initial velocity divided by the change in time, the final time minus the initial time. However, if we assume there's no air resistance, we know that the acceleration, right, of a ball that's dropped near the surface of the Earth, so in the vicinity of the Earth's surface, it's going to undergo, in fact, anything that's dropped, as long as we ignore air resistance, they're all going to have the same constant acceleration, right? It should equal g, should be around 980 centimeters per second squared, or if we were using SI units, it would be 9.8, right? Meters per second squared. That's the magnitude, and the direction is actually negative, but we're just talking about magnitude. Okay, so in this case, we have the initial velocity, think of it as VA. We have the final velocity, the velocity at photogate B, VB, and we know the time it takes to go from VA to VB. So we have that time interval. So really all we're doing, and this is it, this is where the formula comes from, it's simply going to be the final velocity VB minus the initial velocity VA. Okay, so that's a change in velocity, right, from the first to the second photogate, divided by delta T12, because that's the time interval it takes to go from the first to the second photogate. And that gives us the acceleration, which we know in this case is g, right? It should be that constant value of around 980 centimeters per second squared. So very simple, change in velocity over change in time. That's how we're going to find this, the acceleration due to gravity. Okay, now initially, if you notice here in this picture, I also have delta T01. This is just the time it takes for the ball to fall the first 15 centimeters. Well, we need to actually calculate that time. We need to measure that time, the time for the first 15 centimeters to go from the ball dropper to the location, the first photogate. So the first setup here is a little bit different. So think of this as like sort of the initial setup. I put photogate A right before the ball triggers it. So right at the ball dropper, just before the ball triggers it. And in photogate B, I leave at 15 centimeters below. And I want to know the time it takes to go from photogate A, which is like right from the ball dropper as soon as it's released, to photogate B. So basically, I'm getting the time for it to fall the first 15 centimeters. And we're calling that delta T 01. 0 meaning right at the ball dropper, 1 meaning the location of that, ultimately the location of that first photogate. Okay. So you're going to collect the data, right? Again, if you're watching this because you missed this lab for some reason, make sure you get this data from your lab partners, okay? And if you, for some reason you can't get the data from your lab partners, send me an email and I can give you this data that you need here. So we're going to do 5 trials, and these, you're going to fill in the table here, and these are going to be the time it took to fall, the ball to fall the first 15 centimeters, okay? The delta T10 zeros, so 5 trials. Then you're going to answer question 1. Question 1 is going to ask you to calculate the average. Okay, so the average time, so the average delta T01, the average time for the first 15 centimeters. And also it's going to ask you to compute the percent experimental accuracy for that time. So remember, how do we do that? We have to first find all the absolute deviations, find the average absolute deviation, and then finally, if we take the average absolute deviation divided by the average time times 100, that's going to give us the percent accuracy. I know it may have been a while before, since you last computed percent experimental accuracy. So let me jump over to the iPad and give you an example on this. Okay, so let's say that these were the 5 values that we got for the time. So we did 5 trials. You know, in theory, they should be exact, but they're not going to be exact. It's an experiment. There's going to be some error. So let's say these are the values that you got. So these are my delta T01, which are in seconds, right? The time for the first 15 centimeters. Let's say I got 0.1524. By the way, you want to use all 4 decimal places. Then let's say 1497. Kind of just made up these values for this example. Say 1535. Then 1551. So 0.1551. And then finally, let's say 0.1520. Okay, so first of all, remember the resolution of the instrument in this case is based on the number of decimal places. And we can see that the resolution is going to be 0.0001 seconds, right? That would be the smallest time that this photogate and timer system could measure. Okay, so how do we compute percent experimental accuracy? Well, remember the first step is to average these 5 values, right? And if you do that, if you average them, you're going to get 0.15254. But then, and this is very important, you have to round this average to the resolution of the instrument, which means round it to 4 decimal places. So we're going to round it to 0.15, and it would be 25. Right, since the 4 is less than 5, I round down. I get just chop off the 4, it becomes a 0. So that's my average delta T01. That's the average time of the first 15 centimeters. Okay, the next step, remember, I have to create the second column of absolute deviations. These are also in seconds. And remember, that's how far each data value is away from the average. So remember, the way you calculate that is you do absolute value of, take your first data value, subtract the average, and then take the absolute value of that. Well, 0.1524 minus 0.1525 is negative 0.0001, but when I take the absolute value, it's going to be positive 0.0001, right? The next one would be like 0.1497 minus 0.1525. Well, that would be what? That would be negative 0.00, I guess, 28. but then absolute value makes it positive 0.0028. Then I do it for each of them, right? And a lot of times you can just do this in your head, like how far is that 1535 from 1525? Well, it's 0.0010, right? The last, the thousands and 10,000 places, a 1 and 0. So this is going to be 0.0010. The next one, I guess, would be 0.0026, right? 51 minus 25 is 26. And then finally 0.1520 from 1525 is when I take absolute value, is going to be 0.0005. Okay, next, we average all these absolute deviations and then round to the resolution of the instrument again. Well, it turns out if you average these, you're going to get 0.0014. And that already is, right, 4 decimal places. That is the resolution. So we're fine. We can leave it there. Then we're almost done. The last step, remember to find percent experimental accuracy. In this case, for delta t01, I'm going to take my average absolute deviation, so 0.0014, divide by my average time, right, my average delta t01, which is 0.1525, and then simply multiply by 100 to make it a percent. And if you work this out, it ends up being just about 1%, just under, like 0.92%. Remember, the lower the better, right? It means that it's less variable, it's more precise. It's a 0.92%. Okay. And remember, even though it's called percent experimental accuracy, it's a measure of precision, right? It's a measure of the variability. Okay, hopefully that, if you had forgotten some of that, hopefully that cleared it up. All right, let's go back to the handout. Okay, so again, question 1 from the lab manual is simply find this average and then compute the percent experimental accuracy. Okay, then we have the data collection for the main part of the lab. So now photogate A is moved so that it's 15 centimeters below the ball dropper, and it's going to stay there the entire time. Photogate B is going to be at a certain distance below photogate A, and that's what this delta x12 is. So actually there's 5 conditions. The first condition, it'll be 10 centimeters below photogate A. The second condition, photogate B will be 20 centimeters below photogate A, then 30, 40, 50. Okay. If I want to know the total distance from the ball dropper to the second photogate, which I'll need later, I simply add 15 to each of these, right? 15 plus 10, 15 plus 20, and so on. So it'd be like, 25, 35, 45, 55, 65. Now for the times, we already have this, right? We have our average delta T01. That's the time just for the first 15 centimeters. Delta T12 is the time it takes to go from photogate A to photogate B, right? From the first photogate to the second photogate. And that's going to depend on, how far down photogate B is relative to A. So that's delta T12, but it's a time between the photogates. And then finally, later, we're going to also need delta T. So I call this delta T, and that's simply going to be the time from the ball dropper all the way to photogate B. And how do I find that? I can simply add delta T01, right? The time for the first 15 centimeters plus delta T12, depending on what condition I'm in. And that gives me the total time from the ball dropper to the location of the second photogate. So in this case, there was a bunch of data that you had to collect. Again, you want to watch that video on how I actually collected the data. And if you're watching this because you missed lab, make sure you get this data from your lab partners, okay? And if you can't for some reason, send me an email and I can get you some data. And each of these values, again, should be to 4 decimal places. Okay, now what do these represent? So again, this is the first condition when photogate B is 10 centimeters below photogate A, right? There's 3 trials. I'm gonna have you do 3 trials. And what you're finding is you're finding 3 times. And actually you're doing a single ball drop. So you're dropping the ball once and you're finding 3 values 3 different times with 1 single ball drop. You're not doing these separate. You're doing a single ball drop and you're finding 3 times. What do these times represent? Well, delta T12 we already know, right? That's the time it takes to go from the first photogate, so photogate A, to the second photogate B. So that is that time it takes to go between those two photogates. This delta TA, this is simply the time it takes the ball, right? So it's like a little marble. That's the time it takes the diameter of the marble, so the size of the ball, to pass through the first photogate. That's what we mean by delta TA. And then delta TB is the time it takes the ball, the diameter of the ball, just to pass through the second photogate, to pass through photogate B. So with a single ball drop and using, the timers, the CPO timers, you can get all three of these values. Okay, and again, this will make sense if you were in lab, you would have done this. If not, you need to get the data from your lab partner. All right, so question 2 is simple. Actually, it asks you to find the average. So remember, we have 3 trials. So you need to find the average of each of these values. So all 15 values here, find the averages. In the lab manual, it also says compute the percent experimental accuracy, like to estimate it. Don't worry about that. Just find the averages. So for question 2, just find the average of each of these values, okay, in this table here. Okay, question 3. We have this new table, and what we need now is we need the total time, delta T, from the ball dropper to the second photogate. So remember in the picture here, delta T, to find that value, the total time from the ball dropper all the way to the second photogate, I need to add the time for the first 15 seconds, or 15 centimeters, sorry, which is delta T01. And I have that because I have that average right here. Remember, that average is the time for the first 15 centimeters. That's my delta T01. And I need to add that to my delta T12 average. Okay, and that value depends on the condition. So like in the first condition, when delta X12 was 10 centimeters, this would be the average I want to add it to. And in the second condition, where delta X12 is 20 centimeters, I want to add delta T01, same value from above, to this average now, which is right here from this table, right? So my average delta T12 for that condition, and so on and so forth. So I'm getting delta T for all 5 conditions, right? This is the delta T for all 5 conditions. And again, each one is going to be delta T01, which is the same for all 5, plus delta T12, and that's going to change for each of the conditions depending on the condition. Okay, now question 3 is going to have you do a plot where on Pascal Capstone, you're going to plot position of the ball. Think of like downward as being positive. So this delta X is really the position of the ball relative to the ball dropper downward versus time. And in this case, you also want to include 0, 0. Okay, so you're going to plot, if you want to make note here, this is on the y-axis, delta X on the y-axis, and delta T, the time, is on the x-axis. And don't forget to also include 0, 0. Now, what should you find? Well, we're plotting position versus time. We know that the ball in this case is undergoing an acceleration. In fact, it's a constant acceleration. That's the whole idea, is to try and find G, which means its velocity is increasing, right? So that means if you have a position versus time graph, the slope should be increasing. So given that information, you should be able to figure out like what the shape of the graph should be. And that will determine like what you want to do as a fit to the graph. Okay, if it's linear, you do a linear fit. If it's a parabola, you do a quadratic fit, and so on. Okay, so don't forget to, there's basically a question too in the lab manual. It says do that plot, and then also answer the question, what can you conclude? Like, what is it, basically, what is the shape of the graph? Does it make sense? Okay, then we get to the next question, which is really question 4, and that involves this table right here. Now, you already have a lot of these values. So there's 5 conditions, right? This is basically the distance of the second photogate B from photogate A. Remember, it was 10 centimeters and 20, 30, 40, 50, so 5 conditions. And these averages, the average delta TA for all 5 conditions, average delta TB for all 5 conditions, and average delta T12 for all 5 conditions. You already have those 15 values. They're in this table, right? Those are these averages here. So like this first value, this is the average delta TA for the first condition when it was 10 centimeters. Then if you go to this column, this is the average delta TA for the second condition, then the average delta TA for the third condition, and so on. So these 15 values, you can just put them in the proper places here, right? You can fill in these columns with those 15 values. All right, now in order to compute G, we need to know the velocity at photogate A and photogate B. So how do we get that velocity? We're gonna estimate it by using this information. We remember delta TA is the time it takes the diameter of the ball just to pass through photogate A. And delta TB is the time it takes the diameter of the ball just to pass through photogate B. And we know the diameter. In fact, you're going to use the fact that the diameter of the ball is 1.90. I guess I thought I wrote it here. I didn't write it here. So D here is going to be 1.90 centimeters. So 1.90. And then if you divide 1.90 divided by delta TA, that's going to give you VA. Then 1.90 divided by this delta TA gives you the next velocity. Now, there's a way to check these, right? Remember, photogate A is not moving. So these velocities should be pretty much the same. Okay, as long as your delta TAs, these should be pretty much the same, and you're going to find your velocities are pretty much the same. It depends on exactly how you do it, but you're going to find they're going to be around 180 centimeters per second squared-ish. So around 180. Okay. Now, how many decimal places should you use? I don't know, maybe keep these as whole numbers. Okay, I would keep these as whole numbers when you calculate these. So VA will be a bunch of whole numbers, and then VB. Now, when you do VB, remember VB, the second photogate, is moving lower and lower and lower. So the velocity at B, when it's falling, it should be getting faster and faster and faster, right? So that velocity should be increasing. So you should find when you calculate VB here that these values are increasing. Okay, and again, just round to the nearest whole number when you calculate these velocities. The times will still be the 4 decimal places, but these will just do the nearest whole number. Okay, now that you have all the information, you can calculate G, which was the whole goal of this lab. So how do I find G? Well, I use this formula, right? Remember, it's a change in velocity, so it'll be VB minus VA divided by the time it takes to go from photogate A to photogate B, which we have here, which is delta T12. So if I do VB minus VA divided by delta T12, that's going to be G. Again, let's agree to just round this to the nearest whole number, so no decimal places. So you're going to get all your G's, right? You might get, 950 or 1001, right? Actually, that's not too bad because remember, they should be around 980. So whatever you get, you're going to get your 5G values here. In theory, they should be all the same, but it's an experiment. They're not going to be all the same. There's going to be some variability here. So then what I want you to do, this is the rest of question 4 in the lab manual, is average your G's. That'll be like your experimental G. That'll be your representative experimental value for G. But remember, since all these are to whole number, rounded to the whole number, this average also has to be to a whole number. Then since there's some variability there, I want you to calculate the percent experimental accuracy for G. So I gave you this extra column here so you can find all the absolute deviations, like how far each G is away from your average. Remember, these are all going to be the whole numbers. Then you average these, right? That's going to be a whole number, rounded to a whole number. And if you take that average absolute deviation divided by your experimental G value times 100, that'll be your percent accuracy, right? Just like before. And then I also want you to do, and this is also in question 4, compute the percent experimental error. In other words, compare your value, this is your experimental G, to the accepted gold standard value, which is 980. Okay, and remember how to compute a percent experimental error. You have to subtract your value minus 980, and you take the absolute value, so you make it positive. Then you divide by the accepted gold standard value, so divide by 980 times 100, and that'll be your percent experimental error. Okay. There's another way that we can determine G. We can do this graphically, right? We know, so from class, you know that one of the constant acceleration formulas is that the final velocity is equal to the initial velocity plus the acceleration times time. But in this case, the acceleration of that ball is a constant, right? So this formula should apply, right? Because it's a constant acceleration formula. And the ball is starting from the ball dropper at rest. So basically the V initial or V naught, sometimes we use V naught, sometimes we use VI, that should be 0, right? Starting at rest. So this equation simplifies to the final velocity, which we're going to call the velocity at photogate B. So VB is equal to the acceleration, which we know is G, times the time, which is the time interval from the ball dropper to the second photogate. But you already have this information. You know delta T, the total time from the ball dropper to the second photogate, and you know the final velocity, VB, because you calculated them. So question 5 is fill in this table, but again, you already have these values. So these delta T's here, the total time from the ball dropper to the second photogate, you can pull those values from this table. You already calculated them. So in this table right here from question 3. And then the VBs, you can pull from this table. So these 5 values, because you calculated them in this table. So you're just going to rewrite those values down again in this other table so it's organized better. Okay, then go to Pascal capstone again. I want you to plot velocity versus time. Okay, so VB versus delta T, velocity versus time. So VB is on the y-axis, delta T is on the x-axis. Now, in this case, it shouldn't matter. Like you should be able to include 0, 0, but I think it'll come out slightly better if you don't include 0, 0. So I'm going to have you not include 0, 0 in this case. So you're going to plot these 5 values on the y, and then these 5 times on the x. Now, we know that if we plot velocity versus time, the slope of that graph should be the acceleration, right? And in this case, we know the acceleration should be constant so that the velocity versus time graph should be linear. So you want to do a linear fit. And then when you do that linear fit, the computer program will give you the slope value and you're going to record that value here. That's going to be your experimental value for G, right? The slope should be the acceleration. So in essence, it should be equal to G. Then one more thing for question 5. Now that you have your experimental value from the slope of that graph, I want you to compare it again to the accepted value of 980 by computing the usual percent experimental error. Okay, so just 2 different ways of getting G, one by plotting velocity versus time, the other way in question 4 by averaging the values, right? By computing the change in velocity over change in time for 5 conditions and averaging them. And hopefully you got something very close to 980. If you get like 1,030 or something, or 930, 950, that's all very good. That's fairly accurate for this experiment. Okay, now there's one other way that we can find G, or at least that we're going to do in this lab, and that's by using a simple pendulum. Okay, so it turns out that the period, remember the period is the time for one oscillation, right? If you start on one side, release it, the time it takes to go to the other side and come back is the period, T. Well, that's related to the length of the simple pendulum and G, the acceleration due to gravity. In fact, the formula for the period is 2 pi times the square root of L over G. So what we can do here is we can rearrange this equation, right? You can solve this equation for G. So a little bit of algebra. If you work this out, you're going to find that G is equal to 4 pi squared times L, which is the length of the simple pendulum, divided by the period squared. So we can measure, right? We can measure the length of the simple pendulum and we can measure the period. And once we have those values, we can plug them in and we can compute G. So it's another way of finding G, the acceleration due to gravity. So you can either do this using the wooden pendulums, right? If you went to lab, we actually did this using the wooden pendulums that have the washers right at the end of the string and it swings back and forth, that simple pendulum. Or if you want, you could actually do this using the simulation. So you could do the PHET simulation. That will also work, right? So either is fine. So basically what you're going to do is you're going to adjust the length of the pendulum. So it's 20 centimeters below the pivot point, then 30 centimeters below, 40, 50, and 60. Okay, and if you do this Actually, if you weren't able to attend lab, you should probably just go to the simulation and do this so you can collect your own data here. Then I want you to collect, so this is just like you did for lab 1, right? Where you collect the time for a certain number of oscillations. I think in lab 1, we did 5 oscillations. In this case, you're gonna collect the time for 10 oscillations, either using the wooden pendulums or using the simulation. So these are just the time. So when the length is 20 centimeters, it's the time for 10 oscillations. Then you change the length to 30 centimeters, you get the time for 10 oscillations and so on. Now we want to find the period. Well, here's the trick, right? Remember, we collect the time for 10 oscillations just so it'd be more accurate. But if we take that time for 10 oscillations and divide by 10, right, divide by the number of oscillations, that gives us the period, because that would be the time for one oscillation, which is the definition of the period. So now we have the period, which is the time for one oscillation. Okay, now using this formula, so 4 pi squared L divided by T squared, you can plug in the length, you can plug in the period T, and you can calculate G for each of these conditions. And in theory, it's a constant, right? So it should be the same, but it's an experiment. It won't be exactly the same, but hopefully these will be fairly close. Now, just like you did up above, I want you to round this G value to the nearest whole number. Okay, so you might get, 970 or 1002, whatever it is. So round these to the nearest whole number. Then just like before, you're going to answer 3 questions, 6, 7, and 8, but really all they are the following. Fill in this data table, calculate the average G, right, using the pendulum, make sure you round to a whole number, calculate the percent experimental accuracy. So you have to find all the absolute deviations, rounded to the nearest whole number, find the average absolute deviation, which again is going to be a whole number, and that will allow you to calculate the percent accuracy. And then again, compare your experimental value, which is your average here, to 980, which we're going to consider to be the accepted gold standard value by computing a percent experimental error. Okay, and then that's it for this lab. Great, thanks.